Okay, we're going to get started. Our next session is Application Monitoring and Tracing in Kubernetes, Avoiding Microservice Hell. Our speaker is David Von Thenen. Creating microservices is easy, troubleshooting them is not. This session is about how you leverage Jaeger, OpenTracing, and Prometheus to give better visibility into the distributed nature of microservice architecture in a Kubernetes environment. So without further ado, I give you David.
Cool, thank you. Woohoo! So the guys that remembered to set their clock ahead an hour, and then also sober enough to, well, mostly sober enough to come up to see me talk. So cool, awesome. How's everyone's morning so far? Cool? Awesome. So yeah, we're going to talk about application monitoring and tracing in Kubernetes. Basically, how to avoid microservice hell. My name's David Von Thenen. I'm a developer advocate, open source engineer. I work primarily in the container orchestrator space, so primarily Kubernetes, Mesos, and DCOS. More recently, I've been working in the Kubernetes ecosystem relating to the CNCF projects, the Cloud Native Computing Foundation projects, which we're going to discuss a few of them today. Prior to that, I was working in the backup and recovery solution space, most notably in the VMware space. So vSphere, vCloud Director, and yeah, just doing backup and recovery for that. So the agenda, so we're going to cover why do we care? So why do we care about microservices? What are the difficulties and the positives for microservices? I'm going to do an introduction to metrics just so we can kind of level set. And then we're going to do an introduction in tracing and just kind of get familiar with the terms and terminology and stuff like that. So the majority of the presentation, I'm actually going to hopefully, depending if the Wi-Fi permits, do a live demo. So we can actually take a look at the different UIs that you can use for Prometheus and Jaeger. So you can actually do monitoring and tracing. We'll have a demo, or after the demo we'll have the Q&A. And then after that, for people who are here, we have a cool free giveaway, so slim power bank chargers. And actually there might be more than enough for everybody, so we'll have to see. So why do we care? So microservices are awesome, right? Microservices, they give you the ability to create a single service that fulfills a discrete set of functionality. So as an example, you might be able to create a microservice that handles user accounts, right? Creating a user account, modifying a user account, and deleting one. And then they're also highly resilient and they tolerate failure. So if you have a microservice that has any difficulties or is not behaving correctly, what you can do is you can just kill that microservice and then restart it. And then microservices are highly distributed and highly scalable, right? So if you have a given microservice that is being overloaded, like you have hit and peak usage in your application because of peak hours or whatever, and you need to yeah. Yeah, no, it's all. Guys can hear me? Okay, there we go. I was hoping it would go away, but apparently it's not cooperating. So yeah, microservices are distributed and highly scalable. So if you have a particular, say an API server, like a REST API, and it's being overloaded, and because you're in peak usage, it's 7 p.m. and you're like Netflix, and people are coming home and they're streaming their Netflix. You can easily spawn more instances of your microservice, and then you can basically meet the demand for your customers. And then the other cool thing about microservices are that you have the freedom of technology, right? You can implement one microservice in Go, and then maybe another microservice in Java. And because these microservices can be implemented in different languages, and they're discrete sets of functionality, what you can do is you can have autonomy of dev teams, right? A dev team can go off and build one microservice completely independent of another. And because these teams can work independently, it enables things like continuous delivery, right? Like CDCI pipelines and stuff like that. Now, the problem is microservices can also be your worst nightmare, right? Because they're very complex to build, they're decentralized in nature, and where you have tens of thousands of containers, right, running in your Kubernetes cluster, for example. And because these microservices are all interdependent, they call one microservice depends on another, you have to have clear interfaces between your microservices and documentation for those interfaces, right? If you have a microservice that all of a sudden decides to change its API for whatever reason, a new piece of functionality or maybe a bug, and you don't document that and let the other teams know that depend on your service, you can have things behave really badly. And then there's also the operational complexity, right? So if you have an n number of like 500 microservices, for example, right? How do you deploy this, into your environment, into your infrastructure? And then more importantly, like what do you do when you need to upgrade, right? These are like, if you do an upgrade in your infrastructure, in your Kubernetes cluster, how do you upgrade and keep your application available to your users, right? So these are really like complex operational problems that come along with microservices. And once you have your application actually running, like what do you do? Like how do you understand when a user comes into your like website, for example, decides to add an item to his shopping cart? How do you understand what that trace looks like? How do I get that item into my basket? What microservices does it touch in order for that to actually happen? How do you understand what service, what instance of a service is actually participating in that given transaction? And those are things that are very, very difficult to actually visualize, right? Because you have maybe, like in the easiest case, maybe 10 microservices, but you may have 100 instances of those microservices running in your infrastructure, right? So which ones are actually participating in that transaction? So I actually love this picture right here. So it's actually, I just recently moved to Long Beach. Yay, Long Beach. So this is actually a picture of the port of Long Beach. And it's actually one of the busiest ports in the United States. It's actually crazy how many containers are actually flowing in and out of Long Beach every year. And actually in 2005, there were 6.5 million containers coming in and out of the port of Long Beach, right? And now they're probably capacity constrained and it's probably at that upper limit, but 6.7 million containers each year. I mean, that's a lot. Now imagine you were looking for a single container, right? There's one container out there where it has some piece of illegal contraband in it, and you need to identify where that container is in this vast sea of containers that are there. But you had no idea, like, you didn't have any information about that container, where the containers were coming from. Like, how do you go and identify that single lone container? I mean, it's a pretty tough problem to solve. So why am I bringing all this stuff up? So at Amazon reInvent, Netflix had a presentation called Container Scheduling, Execution, and AWS Integration, where they stated they spawn hundreds of thousands of containers per week. Now that's a crazy number. And so I said in 2005, the Port of Long Beach has 6.5 million containers passing through its port each year. And you break that down per week, and it's about 140,000 containers per week. So Netflix is actually spawning more containers than they're actually flowing in and out of the Port of Long Beach. So why am I making this connection here? So now imagine you're at the Port of Long Beach, and you're trying to find this one container that has this piece of illegal contraband. Now, imagine these containers, these physical containers, appear, then disappear. And then in a blink of an eye, a container jumped from one side of the port to the other side of the port, and then back again. Like, how do you actually keep track of all this stuff that's actually happening? So that's the exact problem that microservices in like a Kubernetes or DCOS or Mesos environment, that's the exact problem that we're actually faced with when we're actually trying to understand how these services are intertwined, like what services are interacting with each other and how they're actually participating in the transactions, what the performance looks like. And so I kind of it's an easy way to visualize all this stuff that's actually happening. So I thought it was a cool thing. I just moved to Long Beach, so yeah. So the other problem is like what happens like when you have an error, right? So if you have an error where a microservice just falls over, That's actually a pretty good error because in the whole microservice like infrastructure architecture, if a microservice falls over, a container orchestrator like Kubernetes will just say, oh, I noticed that this container has fallen over. It's dead. It's no longer participating. I'm going to create another container on another host and just bring it back up. Now, that's an easy failure. Now, what happens when the performance of a container that contains your microservice, what happens when that performance actually starts to degrade? Gets slower and slower and slower. That can actually drag the performance of the rest of your application down. So, like I said, errors come in many forms. So some failures are obvious. Cool little picture I found. So other failures are not so obvious. They take a little bit more introspection and attention to try to actually find, right? And because of the distributed nature of containers, how do we identify who's actually talking to who? How do we trace a single transaction through your entire software stack, through your application? And I kind of already alluded to this earlier. Ultimately, a single bad instance of a microservice, single instance of a single microservice can actually spoil the entire bunch, right? How do we go identifying that bad apple in the bunch? So traditionally, a lot of people, what they normally would do is, if I'm having a problem with a particular application, particular service, they say, give me a log file. Let me see a log file of like what's going on and with this particular app. Now, log files are great. I love logging. They give you an easy way of actually finding the root cause to your problem. The problem with logging is they're not great in a distributed environment, right? Because if you have like 500 microservices and you have 100 instances of each of your microservices, you're talking, potentially tens of thousands of applications that are generating log files that are out there in your Kubernetes cluster. So one way that we started to, hey, we can do things like log collectors. We'll have a log collector that'll take all the logs off all these systems, forward them into a central place so that they're easier to get to, right? And that's actually, that's awesome, right? It's a great way to get your logs in one place, all your audit logs and everything in one place. Even with that, right, the problem with logging is that you have all these logs from all these different microservices that are kind of like spread out everywhere. You have these aggregators that are aggregating it all in one place. How do I find what individual microservice among the sea of all those logs are actually giving me the problem? And even with that, they were like, okay, well, now that we have all our logs in one place, like we can do things like indexing. Like, hey, let's start indexing the logs. There are great things that can do machine learning. We'll take all these log files and we'll start like breaking them down as they start streaming in, and to help us identify the problem. Even with that, those types of technologies, the real problem is you still have an individual person doing search to try to find out like where the problem is. You still have a person that needs to go start drilling down into like maybe this service, that service, which log file, start doing a search among, basically a Google search for all your logs, right? There's still a human that's actually trying to dig in through all these log files, searching through them, right? Now, when you have hundreds, tens of thousands of instances of your microservice, the problem with that is you have this living, live environment, right? It's out there in the wild, you have it in production. When you have that many instances and you have one microservice that could actually bring down your entire system, you need to have visibility in your Kubernetes cluster like immediately. It needs to be obvious, and it needs to be instantly visible to the people who are actually trying to troubleshoot the problem. So the cool thing is that there are actually some answers to these problems, right? So the first one, like as we kind of already talked about in the agenda, right? We have metrics and tracing. So what metrics does is it gives you the ability to measure properties of a given system. And based on those measurements, you're able to create alarms and notifications for different behaviors or different errors or different slowdowns within your given application. And then there's also tracing. Now, tracing, what it does is it gives you the ability to observe interactions at the request level. And because we're observing these interactions between various microservices, you're able to look at those interactions based in time, right? So we actually can find out how long something takes to actually execute through your system. So we got a little introduction to why all this stuff is relevant. And now we want to give you a brief introduction into metrics. So what are metrics? So I kind of already had stated a little bit, but metrics are a quantifiable set of measurements of a property for a given system, process, or component. So you often hear the term performance counters or instrumentation thrown around. It's kind of like all in the same category. As an example of what a metric might be, so say you have like a REST API, and you want to know how many API calls, or how long an API call takes to complete. Or as another example, you might want to know how many active sessions are actually active right now in your given REST API. But the idea of it is you record these properties, you observe these behaviors, and then you're able to take those observations and basically react to those changes. So one such tool that's awesome, that's great in Kubernetes land and the Kubernetes ecosystem is Prometheus. So Prometheus is an open source systems monitoring and alerting project. It's a tool. It's actually in the Cloud Native Computing Foundation. It's a hosted project by the CNCF. It was originally built by SoundCloud. So SoundCloud started this, they developed it, and they open sourced it to the community. And what Prometheus really is, quite simply, it's just a data model with time series data associated with it. And like I said, it's open source, so it's available on GitHub there. There's the URL, there's the documentation's there, the source code. You can go ahead and take a look at it. So let's go ahead and deploy it right now. I actually have my Kubernetes cluster in GCE, and so we're actually going to connect in. Can you guys see that? I'm actually copy and paste. Can hear me? Yes? Okay. So I just connected to my Kubernetes controller here in GCE. Just to prove that it's actually live. So there's nothing there. So I have nothing deployed to my Kubernetes cluster. And what I'm going to do right now is using Helm. And Helm is basically a cool little utility tool that gets added on, installed separately from Kubernetes. And what it is simply, think of it like as an app store for applications, but in Kubernetes land, right? So I'm going to use Helm to install Prometheus. You don't need to jot all this down. It's actually on my GitHub page, so you can actually reproduce this later in your own thing, right? So I just deployed Prometheus and Kubernetes using Helm, and I'm just going to do a kubectl get pods. I can see that it's being installed right now. And the reason why I'm doing this ahead of time, it actually does take a significant amount of time to actually get going. So I'm going to install as we go, and then hopefully when we get to the end of the slide deck, it'll actually be running and we'll actually be able to use it. So. Okay, cool. So Prometheus is hopefully installing correctly right now in the background, and I have a cool little architecture diagram because you always need one of those in a presentation, right? So I'm just going to kind of go over the individual components of Prometheus and kind of tell you what they do and like why they're important. So first off, you have the Prometheus server, which is the little box in the center. To configure it, it's actually pretty simple. In Kubernetes, it's just a simple configuration file in the form of a config map. And Prometheus has a bunch of different like auto discovery services that are built in. So if you have stuff in GCE or AWS, or even like if you're doing like Kubernetes on-prem, they have auto discovery mechanisms to find out like your different GCE nodes, your different AWS nodes. The nodes, if you're on-prem, like with Kubernetes, identifying like where your Kubernetes nodes are. And then in order to surface metrics into your Prometheus server, you need to take your application, you import the Prometheus client library, and from there it automatically creates an endpoint for metrics to be surfaced, and then you just need to basically define those metrics, and then they'll automatically get pulled from your microservices and then pulled into the Prometheus server. So they basically use a polling mechanism in order to do that. Now that's great for like long-running microservices, things that are very short-lived that kind of like pop up and go away. They have something on the left-hand side called the push gateway, which is effectively kind of like a service proxy, where if you have an application that comes up, does some form of work, and then goes away, that app can actually push stuff to the push gateway, in which case Prometheus then can take those metrics and pull from that gateway. And so it's a way for Prometheus to deal with very like things that go away, that are transient, that come up and go away. And so Prometheus is sitting here polling to get all these metrics. And you want to be able to do something with those metrics, right? So on the right-hand side, you have something called the Alert Manager. So the Alert Manager, what it does is it's effectively like a rules engine where you can take the different metrics and then perform certain actions based on the behavior or the metrics that you're actually seeing in your microservices or your application. Cool, I think that covers everything. And then, also for the service discovery, if they don't have support for your given like infrastructure or whatever it is, you can actually create a custom discovery mechanisms in order to like discover like whatever special kind of application infrastructure or whatever you have. Oh, question. Yeah, so, it's a perfect question. So the configuration file for Prometheus, that is where you actually define where the things you want to pull metrics from. So if you have your microservice or many microservices that are out there, you import that Prometheus client library. It exposes an endpoint. It's basically, I think it's like REST-based. It exposes that endpoint, and in the Prometheus configuration file on the server, you say, this is where my microservice is, right? This is how I get to it. So it's a fully qualified URL with the like /metrics is usually the default. And in that configuration file, the Prometheus server knows that well-known URL because you actually configured it in that config file, and it goes out and pulls the different services and applications that you have in your Kubernetes cluster. Right. So I kind of have already assumed that you're very familiar with Kubernetes. So Kubernetes already has a built-in DNS mechanism where, so if a container goes away and moves to one side to a new piece of compute, it already has the same fully qualified name. And so no matter where it is in your Kubernetes cluster, it's automatically going to follow it, right? So these are the...
Sort of suggests that there's this life
Well, I mean, you have.
Garbage collected at some point, right? Spawn it, you manage to garbage collect it.
Right. So like the question is like, what happens when you spawn too many services? I mean, in a Kubernetes environment, you have to have, right, container or microservice runs on some form of compute. Whatever the max or the ceiling for like the resources that you need, so that's compute memory, whatever your like watermark is for that ceiling, you have to have enough compute in order for that to satisfy the number of containers at peak that your Kubernetes cluster needs to run. Does that make sense, right? Yeah. Right. Oh, yeah. And there are many different types of containers. Like microservices tend to be long-lived, right? They kind of come up. They're serving like API requests or whatever. And then there are other ones where they're transient. They come up and they go away. And those ones are easier to deal with because they come up for a few seconds and then they go away, do some form of work, and then disappear. It's the ones that are long-lived where you have to be sure that you have enough compute in your Kubernetes cluster in order to satisfy that everything can run. And then if you don't have enough compute, you add more. Any other questions? Oh. Yeah, actually, when I kicked off the Helm install command for Prometheus, it's right now in the background. Hopefully, it's running. It's installing a two-node highly available Prometheus cluster right now, and you can configure that. It's all in the Prometheus chart for Helm. So the different types of metrics that Prometheus supports. So there's 4 main ones. The first one is a counter, which is very simple, right? It just counts from 1, 2, 3, and it only ever increases in value. And so like an example of this type of counter, like why would you use it, is like how many HTTP requests have I served, right? That would be a good example of one. A gauge, which is effectively a value that can go up or down, right? And so as an example of like as an example of a gauge for a given metric, might be like the number of active HTTP or number of active REST sessions that are actually in your application, right? How many people are still actively using your REST API? And then there's one called a histogram. So now we're getting a little more interesting and difficult stuff. So a histogram is basically taking samples of observations and dropping them in buckets. So as an example, like HTTP response sizes, right? HTTP response sizes can be very, very small, or they can be very, very large. And so what you do is you create buckets, maybe like less than 1K, 1K to 10K, 10K to like a meg, and whatnot, right? And based on the size of your HTTP responses, the metric will, Prometheus will drop, the Prometheus client will drop whatever HTTP response size is into those buckets. And then they have another one called summary, which is basically a histogram, where it gives you the summation over the number of instances that are placed into your bucket. So if you wanted to know like HTTP response size, but also the average of that, the collective average of those HTTP responses, so that you'd use something like a summary. So kind of discuss the 4 ways of how you can collect metrics, like the different types of metric types. So based on those types, what you can do is you can create rules based on the observation for those metrics. So, and that's done through the alert manager in Prometheus. So what you can do is you can create like, if you notice your service is starting to slow down, you can create an email alert to like an IT administrator or whatever and say, hey, I noticed a slowdown in the system. Or if you have something where something's completely fallen over, I don't know, and you need immediate attention, like there's Slack. You can create an alert that says, hey, something's wrong, and it's going to put it into like an administrative Slack channel or whatever. And then there's another one where you can do is like webhooks. So you can actually have an alert call out to and do like an HTTP like post, for example, out there in the interwebs. Now, Prometheus does a lot more alerts than this. I just kind of use these as examples. So you can go look at the Prometheus documentation and take a look at the different alerts that are available. So why do we care about alerts? So alerts give us the ability to react to certain things. So one really, really cool use case is, I kind of already talked about microservices and how you can scale them up and down. So say you have a REST endpoint that handles like account creation, and you notice for whatever reason you have a huge flood of users being created at a given time, and you notice that your REST API is starting to slow down, right? You've created a metric to find out what the average response size or average response time is for your given microservice, and you notice the number is starting to slow down because it's being inundated with requests. Now, you can create a rule that says, hey, if the response time for this REST API call starts to slow down, create a webhook to call into my infrastructure to scale it up. And then you can create another rule that says, hey, if I notice that the number of requests are starting to die down, create another rule that can scale back the number of instances for your microservice. So it gives you the ability to dynamically scale up and down, as an example, like a REST endpoint, right? There are many other use cases for it, but it's just a really cool one that you can go ahead and implement. Yep. No, I think there is an SMS alert. I'm not entirely sure, but you can check out the documentation. It's there. I mean, they have like literally, I think, 25 to 30 different alerts that you can do. And then if you have one that you are interested in that they don't have, you can go ahead and create one too, and plug into their framework. So, Prometheus, right? It has 15 official language bindings. And there's also a ton of community-supported ones. I just listed a couple here, like Go, Java, Python, like the big ones. You can go ahead and check out the Prometheus documentation, and you can take a look at all the different client libraries that are available. So just out of curiosity, who here is familiar with like the idea of metrics and stuff like that? Okay, cool. I kind of wanted to jump over that really quickly because tracing is probably the one that's less familiar. So I want to kind of talk about that a little bit more. So we're going to talk about tracing right now. So what is tracing? So tracing enables observability of a given transaction as it moves through a system. And because we're talking about Kubernetes right now, like tracing and metrics in Kubernetes, it's basically allows you to follow a transaction in a distributed system, right? Because Kubernetes is multi-node, has compute nodes everywhere. How do I find out what services are what instances of a particular service are participating in a given transaction? And it allows you, tracing gives you the ability to visualize what instance of a given microservice are involved. And it tracks that path, what services are actually involved through the entire software stack. And it also records time, but it's based on time, right? How long did it take for this given service to complete its request to hand it off to the next microservice? So another component that we're going to take a look at today is called Jaeger. So Jaeger is an open source distributed tracing system. It is a cloud native computing foundation hosted project. It was originally built by Uber. So the guys, you probably took an Uber here, maybe some of you. So they're using it, they built it. It's OpenTracing compatible. So what OpenTracing is a vendor neutral standard that allows you the ability to drop in and switch between different tracing tools in your application without actually having to rewrite your application. So as an example, if you were using, I don't know if you guys are familiar with Zipkin, but it is yet another open source distributed tracing tool. It would give you the ability to drop in Jaeger in place of Zipkin without actually having to change any part of your application, like the actual code-wise. And what Jaeger does is it allows you to do root cause analysis, like what actual microservice is like slowing down or has a problem, and allows you to observe the performance of the entire system, right? Whether it's from the top, like as a user comes into your application, all the way down to the last microservice and then all the way back out. And like I said, it is open source. It is available on GitHub. There's the URL for it. You can get the documentation, source code, and all that good fun stuff. So let's go ahead and deploy Jaeger. I'm going to use Helm again because it's a really easy way to deploy an application, like deploy and just kind of like step away from it. So I can actually check to see if this thing actually deployed. Hey, it worked. The first one did at least. All right, so did a Helm install for Jaeger, and just to make sure it got kicked off, and it is. Don't worry about the errors. I'll explain that in a little bit. So going back to the presentation. So yeah, use Helm to install Jaeger. So cool architecture diagram number 2. So Jaeger is comprised of a bunch of different components, especially if you're going to deploy Jaeger in like a production type deployment. Jaeger is going to collect data. It's called time series data and tracing data, or sorry, not time series, tracing data, and it's going to store all that data into some backing store. And Jaeger currently supports Elasticsearch and Cassandra. The Helm chart by default actually installs Cassandra, but you can switch between the two. Then there's a component called the Jaeger collector. So the collector actually acts as a funnel where you can actually, if you have different traces coming in from different sources, the collector, which you can have multiple instances of the collector, will basically take all this tracing data that's funneling in, and it'll basically stuff it into the data store in the back end. And how that data, or how that tracing data actually goes from your app to the collector, there's 2 ways of doing that. The first is deploying Jaeger agents, so that's the little component on the lower left. So the Jaeger agent is either going to be deployed on every given host, so that your application can send its tracing data to the agent. Or alternatively, and actually the preferred method, is take the Jaeger agent and actually deploy it as a part of your microservice, so as a sidecar to your microservice. 2 different ways of doing it, Jaeger agent or a sidecar container. And then how your application talks to the Jaeger agent, or even the collector, you can actually talk directly to the collector, is you take the Jaeger client library, import it into your app, and then there's an API that's there where you actually talk OpenTracing, because if you wanted to switch from Jaeger to some other implementation, you actually have OpenTracing that wraps the Jaeger client, and you can create tracing information for that. So how long if you wanted to trace, as an example, if I'm going to make an API call to like Amazon, and I want to trace or to capture how long it takes for that API call to complete. Effectively what you do is before you make the API call, you say, hey, I want you to start a trace or start recording this, and then when I'm done with the call, I'm going to end it. And that's how it actually, right, there's a start and like a length, and then what I'm actually capturing. And so there are terms and definitions for that stuff. So like as an example, I said if you needed to make a REST API call, and let's say this is as an example of a 5, what if it's going to do it again? 5, there's 5 microservices involved in your REST API. So you have A through E, and if you had this REST API depend on 4 other services, the way you would capture that tracing data would be kind of like as an example, like a high-level example. This is what it would kind of look like. So a span So that's on the left-hand side, on the lower portion of it. A span is a unique unit of work that has, like I kind of already said, has a name, has a start time, and has a duration. And spans can actually depend on other spans, right? It's effectively depend on other microservices. And if you want to, you can even get more fine-grained than that. If you want to take a microservice and you want to track different sections of that API call in that given microservice, you can break down and get more granular with like function calls or API calls or whatever. But in the end, at the uppermost level, a span really tracks the unit of work at the uppermost level for the start of your microservice, whatever the API calls coming in, to the end. And if you look on the left-hand side, a trace is basically how it gives you the ability to observe the dependencies of your microservices from any point. So if you wanted to just look at how the interactions of microservice B interact with C and D, that's kind of like that middle layer right here. But if you wanted to see what the interaction between is with all 5 of your microservices, that would be the A through E right there. So you can actually get more granular with what you kind of want to see, or you can like look at the entire system and see, hey, these are all the services that are interacting. This is the amount of time that it takes in order for this microservice to complete whatever it's going to do. And then this is a way to visualize it. So if you take the tracing data that's right here, like how the individual microservices interact with each other would look like the graph on the right there. So right, A calls into B, right? Microservice A calls into microservice B. B depends on C and D, and so B calls into C, gets whatever information that it needs out of C, comes back to B, and says, oh, like depend on microservice D, and I'm going to make some API call in order to fulfill whatever it is I'm doing, and it pops back out to B. And notice that the time it takes for B to complete is the sum of C and D plus any like overhead or whatever other computation that it's doing. And then once B is done, it's going to say, here's the information that you requested microservice A. And then it says, but I need some additional information from microservice E. It's going to call into E, return whatever data it's going to provide, back up to A, and then A says, I have exactly what I need to fulfill that given like API request, for example, and it's going to take that data and it's going to surface it back up to whoever called it, right? Any questions?
It's a dependency graph, but it has no sense of parallelization. You can't do...
I made this very simplistic just so that we could, but yes, you most definitely can't have a different parallel process or parallel threads going on or whatever. If you needed to spawn like 10 requests at once or whatever, you can trace all that stuff through the system. Yeah, and you can visualize that in the UI.
Given the intel is in the news, can you do speculative tracing?
No, because it's basically what this is doing is it's actually recording the interactions as it happens.
Okay. Oh,
Yeah.
Are there any, like, to get into the function level type stuff inside of whatever programming language you're using, is that something that there's like an off-the-shelf Prometheus plugin or whatever it needs to do? Or is that something that's only theoretically possible?
So actually, here, let me go to that. So there are 5 official API bindings or language bindings for Jaeger. There's a bunch of community-supported ones, but there just happens to be these 5. So Go, Java, Python, Node, and C++. You can read more there. But yeah, so you're effectively using their API to do whatever you're going to do. So if you need to do something in parallel within your microservice, within your app, you're going to, if you're going to do something in parallel, like before every like function call, for example, you're going to create a name, right? A name for the piece of that unit of work that you're going to do. Like so, like work 1, 2, 3, 4, 5, and then call your function all in parallel, and then you say like, I'm done with what please close out this like transaction kind of a thing, and it all get recorded as underneath like B, you'd see like 4 instances or 5 instances of C where you can actually track like what's going on. Any other questions? Yeah. Yeah, I drew this so that it's all serial, but it doesn't have to be like that. Okay, yeah. So great question. So the way this all works, so I kind of skipped over that. That's my bad. So there's context that's actually being passed through the entire system here. And so that's how it knows to stitch the different things together. The cool thing is it's super trivial to actually do. Most of the library actually does the work for you. The only thing you need to do really when you're building your app to actually capture this tracing data is create a unique name for your unit of work. So like microservice A, microservice B, or whatever. And the context is already handled in the library, and it'll basically get passed down through your different service calls.
Is that managed at the proxy level?
Sorry?
Is that managed at the proxy level?
Proxy level.
Envoy. You've got Envoy sidecar.
Yeah. So the library, the Jaeger library is handling all this stuff, communicating with the agent, the collector, and its context is being passed. So if like microservice A is going to depend on B, when you call B, you're actually passing in the context from A to B. And so it basically follows, just like the dependency graph here, all that context is being passed around until it finally is done with A. And then actually at each point, it's being passed to the Jaeger collector. But
So microservice B has to know how to handle
microservice B has to know how to handle.
the context of Jaeger's tracing recipe.
Yes, but it's handled for you in the library. Like you're not aware that that's actually happening. But it is happening behind the scenes. Yeah. Any other questions?
So, Jaeger, in the context of Kubernetes, off the shelf, is it possible to just scope down the tracing to a particular namespace within Kubernetes cluster? Or is it more about
Yes, but you'd have to build that into the naming for that particular piece of work, right? So if you wanted to namespace it, you'd have to actually, in the name for that given span, so that name for that given unit of work, you'd have to like prefix it with like default or cube system or whatever, right?
And thus, the client had a performance overhead.
Sorry, what?
The client, every client, would have a performance overhead.
Yeah, if it's doing work, I mean, there's going to be some overhead to it. It's not that bad. It's far worse to have the small hit that you're going to take in order to do the tracing than it is to have no information whatsoever at all, right?
Can you speak numbers, like, I don't know, percent-wise?
It really depends on how much you're capturing, right? If you can create, like if you say you have one microservice and it's just one microservice, you can actually capture tracing data for every function call that you make, right? So if you do something like that, obviously you're going to take a larger performance hit than if you were just to actually do a start and end for that microservice, right?
Thank you.
And it's not, and I should also add, there's a transaction close. So when you close it is when it's actually capturing all that data. So if you are doing that frequently, then you're going to take a larger performance hit, right?
If your microservice fails, you don't get any tracing.
At the point of that microservice, yes. you would be basically missing that. But if you had a parent microservice that is calling it, you'll notice that all of a sudden, like, it just stops responding. And so kind of the talk is you need both metrics to actually see that the microservice is actually like being responsive and still running, and you also need the tracing data in order to actually find out how responsive it actually is, right? And what individual components are actually participating in that given transaction.
So the super service get that on a contact, or do you have to do polling, or do you have to know how long you're...
So Prometheus, to actually collect metrics, is doing polling on your services. Jaeger is actually pushing data to the collector. So as function calls are happening and you close out spans and transactions, it's pushing that information to the agent, or you're pushing that directly to the collector. So as it happens, you're collecting the information with your transaction, right? And we're gonna see this. I'm trying to build up to this demo so we can actually see what's going on and like look at the UI and understand like what's going on. So yeah. Actually, I kind of almost already summarized the slide in the talk a little bit a second ago. So metrics versus tracing, right? So just wanted to this is metrics and this is tracing. So metrics is singular per node, per instance, per component view of the world, right? You're going to collect performance, behavior for a given system, component, microservice. Within your microservice, you could have many properties that you're collecting, but the view of metrics is you're only collecting metrics for that individual isolated instance. Now, you could have multiple instances of them, but they're all discretely independent, right? You're collecting metrics on microservice instance 1, instance 2, instance 3, right? They're all separate. But collecting the metrics on those individual components gives you the ability to do health checks, performance monitoring, and et cetera, et cetera, et cetera. And then based on those metrics, based on the information that you're collecting about these individual services, you can create alerts and basically react to the things that are either slowing down or even not responding at all, right? If a microservice decides to fall over, like all of a sudden you can basically have an alert saying, this thing's no longer responding and like what's going on with it, kind of a thing. And we'll take a look at that too. Tracing. So on the tracing side, the tracing is actually what handles the interactions between many different microservices. So that's actually the one that gives you the visibility how these different things interact with each other. So think of it as, I kind of like the best way of thinking about it is, so like you have a normal, how many software engineers, programmers do we have out here? Woohoo, already. So I kind of think of tracing as like a stack trace, right? You have many different like DLLs or .NET things or like Go packages that you're depending on, and tracing allows you, it's effectively like a distributed stack trace. So if you have a component, it allows you to find how this component is interacting with the other components in my application, right? So that's kind of bringing it down to like what a stack trace is, but it's effectively the same thing, but like in a Kubernetes environment, how multiple microservices interact with each other. It's literally kind of like a stack trace, but in a distributed system and distributed environment. You can see how long it takes for a given function or a given microservice to actually complete a given request, and stitch all that stuff together so you can see kind of like a distributed stack trace. So, demo. Hopefully this does not happen. So, yeah, well, hopefully it all worked out. So my demo configuration, so like I said, I have everything up in GCE. I'm running Kubernetes 1.7. There's 1.9 is out. I just wanted to run something a little more stable, so that everything's all good. I deployed Prometheus 2.1, so that's the latest. Jaeger's a little bit behind. I didn't have, unfortunately, have enough time to update it, so we're deploying Jaeger 1.0. And like I said, here's the URL for like running this in your own Kubernetes environment. So that URL is actually this, SCaLE demo, or SCaLE 16 demo, right, the title of the talk. So just kind of some 4 things to mention. It requires Helm because I used it to deploy Jaeger and Prometheus. This is how you actually install Helm in your Kubernetes environment. So I'm like laying this out for you, so it's hopefully the easiest way to get this thing running. You can do a git clone of this repo here, and it's going to give you the other things that are not available in Helm, right? I have the source code for the services that we're going to deploy. So we're going to deploy a simple, very, very simple application that's a microservice like in nature. So there's 2 components that we're going to install. You can find the source code here. You can actually find the Docker file here for the container that I created. And the Docker images are published here. You can go and use them there. To deploy Prometheus, right, I copied and pasted this Helm install command. To deploy Jaeger, I copied and pasted this Helm install command. And all the other information relating on how to run this demo. Alrighty, cool. So let's see if this actually worked. Oh, yes. Okay, so at the top here, you see that we have, can we all see this or no? Yeah? Cool. So at the top here, clear this so that we can actually. So at the top we have Prometheus. You can see that it says 2 out of 2. So it's a highly available Prometheus configuration. We had talked about that Jaeger has a backing store that's either Cassandra or Elasticsearch based. By default, it installs Cassandra. So that's the 3-node Cassandra instance that we actually have right here. I just chose to deploy the Jaeger agent anyways. I actually have 6 nodes, 6 compute nodes in GCE. So we have 6 corresponding Jaeger agent nodes that get deployed to every node in my Jaeger or my Kubernetes cluster. The collector, so that's the one that actually will take all the tracing data that gets sent from the Jaeger or from the application to the Jaeger agent, gets funneled into the collector, and then that gets stored in Cassandra. And then the Jaeger query is basically the UI for looking at all this tracing data. And for Prometheus, the UI is already embedded in the server, so that's, it's already there. I chose not to deploy the alert, so the push gateway or the alert manager. I didn't want to jump into all that stuff because it would require either Slack or something like that. So we're going to look at some cool metrics, hopefully, with this app that we're going to deploy in a couple seconds. So we see everything's running. So one thing I did in order to kind of simplify everything is I deployed everything, instead of having an ingress controller. How many people know what the ingress controller for Kubernetes? Okay. I didn't want to confuse anybody, so I just didn't want to do that. So I'm just trying to keep this as simple as it possibly can. So I deployed everything using node port, which in Kubernetes land is basically just saying, there's a listening port for these given applications that you want to expose out, like a UI, for example. And we want to be able to assign a port that's not going to collide with another port. So if we have the Prometheus UI and the Jaeger query UI both on port 80, we need to assign a different port to both of them. The node port is what does that in Kubernetes land. And so in order to get to the UI, actually before I do that, So take a step back. So we're going to deploy an application, a microservice-based application. It's very, very, very simple. So there's 2 components. The first component is called front end. And front end is just going to offer up an HTTP server, right? Just a way to get at some HTML. Front end is going to call into back end. And back end is very simple. All it's going to do is it's going to do a curl on the Google homepage, so google.com. It's going to take that HTML, It's going to pass it back up to front end, and then front end is just going to surface it to the user. So incredibly simple. And because front end is a web server, we need to go ahead and deploy Kubernetes services, or basically the networking configuration, so that we can actually access front end out, hopefully, here today. So I'm going to do that right now. What's that? So these are actually two separate deployments. So we're going to deploy front end as one pod and then back end as another pod. Yep. So yeah, actually here. So that Prometheus, good question. So we said in order for Prometheus to discover our microservices or applications within Kubernetes, that stuff needs to be configured via the config file. So one of the things that I kind of like hid from everybody a little bit is I actually have Prometheus.yaml right here. And so I already had, within the Prometheus configuration, already had set it up so that it's going to auto-discover based on the services that I'm going to install for Kubernetes to discover front end and discover back end. So if we actually do a cat Prometheus, you can see front end default service cluster local. So that's the way in Kubernetes define the fully qualified domain, or fully qualified name for a given pod in Kubernetes. So there's one for front end and one for back end. And then you can already see that the scrape interval is how often it's going to pull those microservices in order to pull metrics into Prometheus. Any other questions? All right, cool. So let me go ahead and deploy those services, the Kubernetes services. So there's the service for back end. Here's the service for front end. Now what I'm going to do is I had already said that we want to expose these services, so the Jaeger UI, the Prometheus UI, and now front end, right, the HTTP server that's there, out to the internet so we can access it. So in GCE, what I need to do is I need to take the ports that are exposed in Kubernetes and map them to the firewall on GCE so that we can actually get at them here. So I'm going to do that right now. So here's the node port for, the node port for Jaeger. So if you're going to run this in whatever cloud that you're going to run it in, you're going to have to do something similar, right? If you're going to run this in AWS or GCE. And I'm going to take the node port for Prometheus. And then because we have the front end, which is actually exposed as an HTTP server, we need to have that too.
So you're just prefixing these with K and
So no, these are, so yeah. You're asking about the K prefix. So this is just the firewall rule for GCE. So I could have named it anything. It's just basically a way to map the container, the port that's in Kubernetes, the container port, out to the outside world. So when we're actually going to, like, as an example, we're going to pull up the Jaeger and so here's the external IP for, right, yeah, that's what I just chose to name them as. I mean, you can literally name them however you're going to name them for your deployment, whether it's dev, test, or production, or whatnot. So I'm going to take the port here. Hopefully this works. Yes. So this is what the Prometheus UI looks like. We're going to dive into that in a second. And then I'm going to take the UI for Jaeger. Yes. Okay, then there's the UI for Jaeger. So let's just take a look around. So Prometheus, so here's a list of all of the metrics that are currently being recorded on Prometheus. I know I just deployed it, but I had already preset up in the config map, so the Prometheus configuration file, things to already track. And what we actually can do is we can go to status, and we go service discovery. So that's that service discovery component that allows you to discover like GCE instances or AWS instances, or if you're running like Kubernetes on-prem, there's actually a way to discover Kubernetes like pods, nodes, even the API server. And actually that's what I kind of did. So, what's that? I believe, yes. Oh no, OpenShift, yeah, most definitely. So OpenShift it's literally Kubernetes with additional stuff. So yeah, this Prometheus, you'll have to, actually the configuration, the Kubernetes discovery mechanism should be exactly the same for OpenShift, yeah. So yeah, there's three things that were configured in that configuration file. The first one is, well, the last one in the list was the two microservices that we're going to deploy in a second, so front end and back end. So the other one, so number two is we're actually using Prometheus to actually monitor Kubernetes. So we're actually using Prometheus to find out the performance of the API server, the performance of the nodes that are there, individual pods that get deployed, service endpoints, and services. And then the third thing, which I actually kind of think is a little weird but kind of cool, we're actually using Prometheus to monitor itself. So if Prometheus is starting to slow down or do something a little bit wonky, you can actually potentially spawn up yet another instance of Prometheus to handle all this metrics data that's being collected everywhere, right? So if we actually go back to the UI, let's see if we can find something interesting. So these are all the different properties that are being collected through those three different discovery mechanisms. So if we look at like, yeah, API server request latency bucket, let's just go ahead and take a look at what that looks like. So just a bunch of different metrics that are this is the text form of it, and if we want to see hopefully a graph. Okay, not so interesting, but it's a way to visualize kind of all the different, so the four different types of metrics that are the four different types, right? There's the counter, the gauge, the summary, and the histogram, right? And based on whatever metric is best suited for your particular property that you want to capture is the different type that you're going to use in your, in your metrics collection. So there's that, very cool. And the reason why Prometheus automatically has all this data that's being collected, right, is because Prometheus is polling all these different endpoints, right? Now Jaeger, unfortunately, because it relies on push data, when you start up the Jaeger UI, there's nothing really interesting at all because nobody's pushing data to it right now. All right, so we have Prometheus. We kind of did like a cool little, what's going on with that. Jaeger, unfortunately, doesn't have anything interesting at this point. So let's go ahead and deploy those two microservices. So I'm deploying the back-end service, and then I'm going to go ahead and deploy front-end. And then I just want to make sure that it actually is deploying. And they're fairly simple, right? Fairly simple services. So back end right there at the top, clear it out. And then front end just right underneath it. And they've been just started 23 and 16 seconds ago. So what we're going to do now is we're going to do a simple curl against the front end service. And like I said, front end will call in the back end, grab the Google homepage, and hopefully surface that all the way up. So let's go ahead and do that right now. Oops. Oh, did I? Oh, typo. That would be very bad. Thank you. Grab the port for that. All right, so hopefully this will work, and hopefully we get to see something pretty cool. All right, so there's the HTML dump for google.com. Yay. Yeah, it's a lot going on, right? So we have the two microservices. They both pull in the Jaeger client library, and they both pull in the Prometheus client library. And so we're going to go ahead and take a look at what we actually recorded. So if we come back here, and we look at our available properties, we see that we actually have two new properties that are being collected. One's called Cloud Native App Frontend, HTTP request total, and then you have another one for backend. And those things are being reported individually from each of the two separate microservices. They're two separate pods, right? So if we go ahead and click that, and then we do execute, we can see that we have a value of 1 right here. And it corresponds to this one call that we made. And if we go to backend, we can actually see that there's another value of 1 because it's 1-to-1. So not really interesting, but it's just to prove that you can collect metrics for whatever. Now, if we go to the Jaeger UI, and hopefully this works, go to the Jaeger UI, do a refresh, and if we pull down the list of services that are here, we see that we have back end and front end. So in that one dependency graph, you could actually, at any given point, if you wanted to look at how B interacts with the services that it depends on, you can go ahead and do that. And so if I wanted to do that, I could click backend and just find out how backend is interacting with the rest of the system. Or I could do it at the topmost parent level, which in this case is front end, which is what I'm going to select, and see how the entire system interacts with each other. I'm going to go front end. Oh, man.
So that pull down is sequence top down.
No, it's the. So the way it's going to be, it's going to be completely random. There's no like rhyme or reason to it. You can do a search based on the particular tag or name for your span or your unit of work. So I had to shrink it back down so I can find the button. Oh, we can still all see it. Okay, cool. So if we go find traces, and I'm looking at the front end, which is the topmost level for our app, and we actually can see that it recorded 4 spans here. So, and the time that it took was 149 milliseconds. Now, if we go ahead and click that, we can actually see like the total time it took front end to complete, which is that green, guys are horrible with color, but that green bluish color at the top there. And then front end calls into back end, right, which is that next level down right here. And then back end, right, in turn calls getgoogle.com, right? And so it went out, did a curl, pulled that, did an HTTP get, and then sent that to back end. Back end ended up sending it to front end, and then it surfaced it to the user. So this is how an easy way you can visualize what microservices are participating in, like what type of, like how they're interacting within your application. So let's do one more curl. And we see the Google homepage again in text form. Not very interesting. If we go back to Prometheus, I could have just clicked that, oh well. And we look at the number of requests that we done. We see that it's 2 because I did the second curl, and we should see the one corresponding to the back end, which is right. Now, if we go to the Jaeger UI, this is where it kind of gets a little cool, and the whole reason for this. So the second one here is we see that we have yet another trace, right? That's the first one. We did the one about 4 minutes ago, and then this is the one we did a few seconds ago. Now, if we click into this trace, we see that, thankfully, it's almost exactly the same, right? We have front end calling into back end calling getgoogle.com, doing HTTP get, and then returning that information back up. Now, the cool thing is, the first call took 149 milliseconds to complete, but the second call took 115 milliseconds. So it's significantly faster than the first call. And the reason why that is because the first time we made the call, it actually had to do a DNS lookup to get where I'm actually talking to get google.com. And the second one, it was already cached. And that's why you see a performance difference between the two. And so it's little things like that that Jaeger and like Prometheus give you the ability to like actually visualize kind of like what's going on. And that's why like metrics are important. And that's why like combination in concert with tracing, why that's important. It gives you the ability to react to certain things and then also to visualize to see how your different microservices are interacting with each other, how long they take to complete, and then you can see things, little, like discrete little differences, but they're really important differences. And that's pretty much it. So, any other questions? Oh, what's that? Oh.
Yeah, just wondering, how do you deal with the volume of these calls?
Yeah, so each of the components, so Prometheus and all the Jaeger components, yeah, I don't think it was on. So like, how do you deal with the volume of all these the calls and trace information that's being done? Like everything, Jaeger and Prometheus, well, mainly Jaeger because you're talking about a huge volume of information that's different, is Jaeger, all the components of Jaeger can scale out. So it also itself is implemented using a microservice architecture. So if you need more collectors, you throw more collectors on the air.
I mean, is there like any kind of pre-filtering? You like trace every 100th call or something like that? Or?
Oh, sorry, hey, if you guys want your free little prize thing, go for it. Come up here and grab it. It's actually the little charger. So sorry.
Yeah, is there any way to kind of reduce the number by, say, tracing every 100th call?
Yeah, and that's entirely up to your implementation. Yeah, so if you want to do more granular, you can. And if you want to do less granular, you can do that as well.
That's a good presentation.
Oh, cool.
Thank you.
Yeah, definitely. Oh, yeah. I'll tweet it out.
Can I give you my email?
Yeah. And then if you want to reproduce the demo on your own Kubernetes cluster, like I said, it's available on my GitHub. All the source code for front end, back ends, like I said, all the commands in order to run. Yep. Yep, cool.